This is Euclid Book 10, proposition number 91. I want you to take a real good look at this diagram because we're going to be using this for the next 6 proofs. Yeah, you loving that? Yeah, here we go. If an area be contained by a rational straight line in a first apotome, the side of the area is also an apotome. We'll let the area AB, okay, so what's the area AB? That is all of this right across here, from A to C to B to D. This whole thing right here. Not any of this, just this. Okay? So let the area AB be contained by the rational straight line AC in the first apotome AD. So here's AC here, which is the rational straight line. And here's AD across here, which happens to be a first apotome. I say that the side of the area AB is an apotome. Okay. For since AD is a first apotome, since this already is a first apotome, let DG be the annex. This will be the annex right across here, all the way across. Therefore, AG and GD, well, what's AG? That's this whole length right across here, from A to G. That's the first length. What is GD? That is from here to here. Okay. Both of these lines, from here to here and from here to here, both of them are rational straight lines. They are commensurable in square only. This is by Euclid Book 10, proposition number 73. And the whole AG, this whole line across here, all of it, is commensurable with the rational straight line AC set out. So this whole thing is commensurable with this. And the square on AG, which we're going to represent right here. Okay, now remember, on these type of squares, what we do is we take the length of AG and we make it into a square, and all 4 sides of that square are going to be the length of AG. I know that's not what that looks like, but that's what we're going to represent it. Okay, because if we had to really draw this out, it would be great big. You can draw this out for yourself, and I welcome you to do it. So, and the square on AG is greater than the square on GD. So this is greater than this by the square on a straight line commensurable in length with AG. This is by Euclid Book 10, third set of definitions, number 1. If therefore there be applied to AG, okay, we're going to apply something to this line right across here. A parallelogram equal to the 4th part of the square on DG, and deficient by a square figure, it divides it in commensurable parts. Which is by Euclid Book 10, proposition number 17. We'll clear that up in a little bit. Let DG be bisected at E. Now, I know this doesn't look exactly right, but if we were drawing this 100% correct, this line right here would bisect DG. In other words, DE would be the same length as EG. I know that's not what it looks like, but that's the way it would be if we did it correctly. I'm a little sloppy, I'm sorry. Let there be applied to AG. Okay, we're going to apply something to AG. A parallelogram equal to the square on EG. Okay, so what's the square on EG? Well, this is the square on EG. We got this, down here, and down here. Okay, that's your square on EG. So what we've applied to AG here, this whole area from here to here to here to here, that whole thing is going to be equal to the square on EG. And deficient by a square figure. And let it be the rectangle AF and FG. Okay, so what are we going to do to form this rectangle? Here's what we're going to do. First of all, we've represented the square on EG with this. That's going to represent the square on EG. Now we're going to make the rectangle. How do we make the rectangle? Well, 2 sides of that rectangle are going to be the length of AF. Okay, that's 2 sides of it. Now, what are the other 2 sides of this rectangle going to be like? Right here. Okay. Alright. So, the area of all of this is going to be equal to the area of the square on EG, but it's going to be deficient by this amount right here. Okay? Therefore, AF is commensurable with FG. This line here is commensurable with this line. And through the points E, F, and G, well, here's points E, F, and G, we're going to draw the following lines. We're going to draw EH, that's this one right here. We're going to draw FI, which is this one right here. We're going to draw GK, which is this one right here. And all three of these lines are parallel to AC. Now, since AF is commensurable in length with FG, which we just stated earlier, therefore, AG is also commensurable in length with each of the straight lines AF and FG. This whole length right here is commensurable with this length right here. It's also true that this whole length across here is also commensurable with that. But AG is commensurable with AC. This whole length right across here is commensurable with this. Therefore, AF is commensurable with AC. FG is also commensurable with AC. And this is by Euclid Book 10, proposition number 12. And AC is rational. This line is rational. Therefore, each of the straight lines AF and FG. Here's AF, and it's rational. And here's FG, and it's also rational. So each of the rectangles AI, okay, so what is AI? It's this area plus this area plus this area. This whole thing right across here. That area is rational. What about FK? This area right here, all of this and nothing else. None of these three, just this. This one right here is also rational. That's by Euclid Book 10, proposition number 19. Now, since DE is commensurable, okay, DE right across here is commensurable with EG. Across here. This is commensurable with this. Therefore, DG is also commensurable in length with each of the straight lines DE and EG. Okay, so this is commensurable with this, and this whole line is commensurable with that. That's by Euclid Book 10, proposition number 15. But DG is rational and incommensurable in length with AC. Okay, so DG is a rational line. It also happens to be incommensurable with AC. Therefore, each of the straight lines DE, which is this one right across here, and EG, which is this one right across here, this is a rational line. It's incommensurable with this. And this is a rational line, and it's also incommensurable with this. This is by Euclid Book 10, proposition number 13. Therefore, each of the rectangles DH, what's DH? DEHB, that's this area right here. This rectangle right here. And EK, what's EK? Well, EK is this area plus this area. All of this right here is EK. So, this rectangle is medial. This whole thing right here, this EK, is also medial. This is by Euclid Book 10, proposition number 21. Now let the square on LM. What is the square on LM? Okay, when we draw a line, we have this square. Okay, we're going to create this square, and it's going to be LPMR. This is a square. Be made equal to AI. Well, what's the area of AI? Well, that's this plus this plus this. So all three of these areas combined will be this area right here. And let there be subtracted the square NO. What's the square NO? NO. Right across here. This area right here. So, let's read this again. Now let the square LM be made equal to AI, which we just did. And let there be subtracted the square NO having a common angle with it, the angle LPM. Okay, well, LPM is one angle in the square of LM. It also happens to be the same angle of NO. Okay? Now, the area in NO is going to be the same area as this. Okay? Therefore, the squares LM and NO are about the same diameter. This is by Euclid Book 6, proposition number 26. Let PR be the diameter. Okay? PR is the diameter of LM. And let the figure be drawn. Since the rectangle contained by AF and FG is equal to the square on EG, okay, so this has the same area as this. Therefore, as AF is to EG, as this line is to this line, so is EG to FG. So is EG to FG. This is by Euclid Book 6, proposition number 17. But as AF is to EG, as this is to this, so is AI to EK. So this whole area here, okay, this whole area here is to this whole area here. Okay? So you're forming a ratio. Okay? As this whole line is to this whole line here, so as this area is to this area. Okay. And as EG is to FG, as this line is to that, so is EK to KF. Okay? So is this whole area is to this area. So the whole is to this part. This is by Euclid Book 6, proposition number 1. Therefore, EK, this whole area right across here, this plus this here, EK is a mean proportional between AI and KF. Okay? This area right here is a mean proportional between these three areas combined and these two areas combined. This is by Euclid Book 5, proposition number 2. But MN is also a mean proportional between LM and NO. So what's MN? That would be this area plus this area. Okay? So this whole thing right across here is a mean proportional between the whole area across here, this LM, the whole thing, and this little area of NO. As was before proved. That was from the lemma after Book 10, proposition number 53. And AI is equal to the square on LM. So if you add these three areas together, you get the area of LM. And KF to NO. This area is equal to this area. Therefore, MN is also equal to EK. This area here, and these two combined, and these two combined plus this area right, okay. These two combined are the same amount of area as this is right here. But EK is equal to DH. Okay? This plus this whole area right here is equal to this area right here. And MN to LO. Okay, well, what's MN? That's this whole area across here. And LO is this area right across here. This plus this. This plus this is MN. This plus this is LO. Therefore, DK. Okay? This plus this. All this area here is equal to the nomen UVW. Okay? What is UVW? Well, if I'm reading this correctly, it's this area plus this area plus this area. Okay? So this plus this plus this equals this plus this plus this. Okay. I'm a little lost here, so bear with me. Okay, I may be wrong on that. Okay, so it may actually be it may be this plus this plus this plus that. I don't know. They really didn't clear that up very well. Well, Euclid didn't anyway. But AK is also equal to the squares on LM and NO. Okay, well AK, that's all of this area here, is equal to the squares on LM and NO. So it's equal to all this plus that. Therefore, the remainder AB is equal to ST. This area right here is equal to this area right across here. Okay? But ST is the square on LN. Okay. This area here would be the same amount of area as if we had drawn the square of LN. I'll just go ahead and draw the square on LN. Okay. So this area would have the same amount of area as this. Therefore, the square on LM is equal to AB. Okay, so this area is equal to that one. Therefore, LN is the side of AB. So this line right across here is one of the sides of AB. I say next that LN is an apotome. For since each of the rectangles AI and FK, well, where's rectangle AI? Get this plus this plus this. This is all of AI. What's FK? That's this one right here. Both of those rectangles are rational. And they are equal to LM and NO. Okay? So, what is LM? That's all this area right across here. What's NL? That's this right here. Therefore, each of the squares LM and NO, that is the squares on LP and PN. Well, what's LP? LP is this, across here. And PN, well, that's this. Okay, so what we're going to do is we're going to take the length of LP and we're going to turn it into a square. We're going to take the length of PN and we're going to turn it into a square. So, the square on LP is rational, therefore the square on PN is also rational, therefore each of the straight lines LP and PN are rational. So this straight line is rational, this straight line is also rational. Again, since DH is medial and equal to LO, okay, what's DH? That's this area right across here. And it's equal to LO, which is this plus this here. Okay, this area is equal to that. Therefore, the area of this plus this together is medial. That would make the line LO. Okay. No, there's no line LO, I'm sorry. Since the area of LO is medial, while NO is rational, therefore LO is incommensurable with NO. So this whole area across here is incommensurable with this tiny area right across here. But as LO is to NO, as this whole area is to that little area, so is LP to PN. So as this line is to this line. This is by Euclid Book 6, proposition number 1. Therefore, LP is incommensurable in length with PN. This line is incommensurable with this. And that's by Euclid Book 10, proposition number 2. And both are rational. Okay? This is a rational line, this is a rational line. Therefore, LP and PN are rational straight lines commensurable in square only. So the only time that the lines LP and PN are commensurable is if you square them. Therefore, LN is an apotome. And is the side of area AB. So this is the side of one of these four sides. Therefore, the side of the area AP is an apotome. And I'm glad this proof is over with, because that was a very long proof. Alright. I will tell you more in a future video, so I want you to stay tuned.